Okay, so we're going to be talking about thermochemistry. And before we get started, I just want to point out that STP for thermochem is different than for gases. Our STP is going to be 25 degrees Celsius or 28 Kelvin. We don't really use Kelvin a whole lot, so just remember STP is 25 degrees Celsius. Alright, now all actions either release or absorb energy, and we want to measure how much energy we are taking in or giving off. Heat energy is also referred to as enthalpy, or heat of formation. That's where we get the H from in the heat. And it's the change in heat of formation. That's what this delta means. The triangle means change. Our units are going to be joules or kilojoules. Like I said, we can only measure changes in enthalpy. So this is your equation for heat of formation, or for enthalpy. You're going to take your final minus your initial. And since they're chemical reactions, your final is your products minus your initial, which are your reactants. Okay, let's define a few terms. A system is a chemical reaction under study. Chemical reaction under study. So if we're talking about an ice cube melting, we're talking about just the ice cube. That would be our system. Our surroundings is going to be any place in the universe except the system. So any place in the universe So again, if we're talking about the ice cube melting, the ice cube would be our system, and maybe the glass it's in or the room it's in, that's going to be the surroundings. Any other place besides the molecules in that ice cube would be your surroundings. So for exothermic reaction, you probably know this is just a reaction that gives off heat. And when we calculate the delta H for exothermic, it's going to be negative. The sign will be negative. And that will be important. You'll have to recognize chemical reactions. If I say this is the delta H, just by looking, it will tell me endo-exothermic. And if the number is negative, you automatically should know it's exothermic. So an example of an exothermic reaction would be water freezing. As water turns to ice, an ice cube is much colder than liquid water, so that energy had to go somewhere, so it's exothermic. It releases it into the surroundings. The system releases energy into its surroundings. For an endothermic reaction, it's just a reaction that takes in heat. And when you calculate the heat of formation, or enthalpy, the number will be positive. And an example of this would be cooking soup. Right? You're cooking soup over the stove. The stove is giving heat to your soup, and your soup becomes warmer. Alright, so here, an ice cube is melting. So what do you think that would be? Do you think that would be endothermic or exothermic? And it would be endothermic. So if it's endothermic, this system would have a positive, delta H. Forgot my triangle. Okay. And we've got an ice cube freezing. Not ice cube freezing, water freezing into an ice cube, which is exothermic. So if it's exothermic, we're going to have a negative delta H. Negative delta H. So now that we're familiar with what this reaction means, I forgot my delta H. Let's go ahead and do the calculations. So when we're looking up when we're trying to plug in numbers for this calculation, I have to give you a table of some sort with the values on it. except diatomic elements or elements just by themselves. If they're in their elemental state, their value is 0. Otherwise, you gotta look it up on one of these tables. So let's do this reaction here. Liquid water going to gaseous water. And our equation is change of products minus change in reactants. Now, you have to pay attention to your states of matter because they have different values for enthalpy. So our products minus our reactants, so we're going to start with gaseous water. So that is negative 242 minus our reactants, which is liquid water, negative 286, and when two negatives come together, they make a positive. So we get negative 242 plus 286, which gives us 44 kilojoules per mole. And look, my number is positive, right? So this is endothermic, which makes sense, right? You got liquid water that's going to a gas. If you're boiling water on a stove, that system, your water molecules are taking in energy to become gaseous. Yay, math. All right, how about this one? We've got a combustion reaction here. You might be able to guess already what kind of reaction we're going to have. It's going to be the same equation to use, products minus reactants. So our products, we got carbon dioxide, so let's see, it's negative 394, plus we've got two waters, gaseous waters at that, so I need to multiply my gaseous water value by 2, negative 242. Okay, minus our reactants, methane, negative 75, plus I got 2 oxygen molecules, and my oxygen, let's see, is not going to be on the chart because this is diatomic, so it's 0. Okay, so mash that into your little calculator and you should get negative 803 kilojoules per mole. And look, my number is negative, right? So that means it's exothermic. Yeah? And of course, it's combustion, it's fire. Of course you're giving off heat, right? So this, no-brainer on this one. Okay. Second equation you're going to need when you're doing thermodynamics is specific heat. And here it is. Q equals MCAT. That's how I remember it, MCAT, even though that's not a name. Q is heat, just generic heat. M is mass, right, measured in grams. Oops, that's a G. And C is your specific heat, which is usually a given value that you'd have to look up, or they give you everything else and you have to solve for that, but usually you have to be given this specific heat. Or heat capacity, sometimes it's called heat capacity. And what specific heat is the amount of heat required to raise 1 gram of something, whatever it may be, we'll call it X, 1 gram of something by 1 degree Celsius. Okay, that's what specific heat is. The amount of heat required to raise 1 gram of something by 1 degree Celsius. And then you multiply that by change in temperature. And your temperature is always going to be in degrees Celsius. So do not convert to Kelvin. We're going to use Celsius for thermodynamics. Okay? All right, let's try a practice problem here. How much heat, so we're looking for Q, is required to warm 400 grams of water from 20 degrees Celsius to 50 degrees Celsius? So we have our equation, Q equals MCAT, and our mass is 400. Our specific heat is 4.18, and I just happen to know that because I have an open book sitting next to me. Otherwise you would have to look this up, but I did not want to ruin this beautiful slide with an ugly chart. So our change in temperature is always final minus initial. So 50 degrees minus, oops, already starting trying to do math in my head. 20 degrees Celsius. And when you punch that into your calculator, you should get something like 50 joules. So hooray! That is thermodynamics in a nutshell.